Quill pens might be about to make a comeback, but not in the stationers. That's because researchers have developed a nanoscale ink pen that can control the shapes of polymers. These are giant chemical structures made by linking together lots of small molecules. And what Imperial College's Alex Perevedentsev and his colleagues have discovered is that with a dab of nano ink delivered in the right way from their nib pen, they can make polymers adopt specific shapes that alter the way light passes through them. And as he explained to me, this is what we need to make a new generation of much faster microprocessors that use light rather than electrons.
I guess we were inspired by nature, as the best studies are. Plants polymerize glucose into two kinds of polymers. Exactly the same chemical structure, exactly the same order of atoms, but the only thing that is different is the 3D orientation of those molecules in space. So one polymer of glucose is called starch, and it is a curved molecule. It kind of curls up on itself like a banana, and that stores energy. The same molecule, if you polymerize it in a slightly different fashion, you end up with a linear chain. That's cellulose. And the cellulose is what's used to make the physical structure of the plant, so the stems and so on. And we decided to explore this kind of parameter space and to actually use the molecular nature, this chain-like nature of our polymers, to change the way in which they interact with light.
So, for the polymers that you're studying, how does changing the arrangement, the way that these polymers are strung together, how does that change how they interact with light? I mean, does that change their colour? What sort of things are you looking at?
So the crucial thing there is the way that the individual molecules within the chain, the individual chain links, talk to each other. For example, the closer they are or the way they are twisted relative to each other dramatically affects the optical properties, such as, for example, the color that chain emits or absorbs and its electronic properties. And so we sought to take a single polymer chain and find a way to selectively change the way it's twisted in on itself. So maybe we have a part of a chain which is a helix, a part of a chain which is a planar zigzag, a part of a chain which is disordered, and all of these different chain segments would have dramatically different optical properties that we're interested in.
So, how then do you arrange these polymers in different organisations, whether that's a zigzag, a twisty ladder, or just all over the place? How do you actually get them into the conformation you want?
Well, we're very lucky here because the polymers that we work with, they turn out to be incredibly smart, and they like to do certain things. They just need a little bit of an encouragement or some leeway to do them. So what we did is we dug up a pen, and you scale it down to nanoscale, and you end up with an instrument called dip pen or ink pen nanolithography. And so all this allows you to do is to pick your favorite ink. In our case, it was just a simple solvent, and write a line across your film. And writing that line across your polymer film encourages, or even more accurate word would be allows the polymer chains to relax into a new geometry.
So this is almost like, I imagine, the old-fashioned big quill pens, that they're just a little nib and you're just basically poking your polymer molecules around to make them in different shapes.
Exactly. It's funny, isn't it? How do you draw a very small line? We'll take a very small pen. The idea is basically still the old one. We just scale it down to the really interesting submicron length scales.
So now that you can use your polymer pen to arrange these molecules in different shapes that have different properties, what can you do with them? I mean, it's kind of cool, but what next?
When you have your polymer film structured on a very, very small scale, you can play tricks with light. And you can actually write structures on a plastic film that control the way light interacts with it. So the two examples of that would be a mirror and an optical fiber. So we can take a polymer film or plastic film on a bit of glass, and you can write this very complex network of waveguides or optical fibers. And this would be very interesting for designing the next generation of optical and electronic circuits.
Would these be faster circuits or better circuits than the current circuit boards we have?
These would be, in principle, faster by orders and orders of magnitude. It's hard to imagine the world where these are a reality, but I think we're going that way.
And it's amazing to think a little pen pushing polymers around could be part of a supercomputer of the future, a light-powered supercomputer.
Exactly. Yeah, it's a funny idea, but that's exactly how it works out.